Assalamualaikum and a very good day. My name is Muhammad Muhsin bin Hashim and I would like to present my thesis titled Characterization of Oil Palm M3 Fruit Punch Mixed Low Density Polyethylene PEFB LDPE Polymer Composite for Deck Panel. My supervisor Dr. Noraini binti Masri and my co-supervisor Dr. Mazlana binti Ma'in and TS Saiful Rizal bin Masrur. Okay, my presentation outline will be the first is introduction, followed by problem statement, research objective, research scope, literature review, methodology, and result and discussions. Okay, as an introduction, natural fiber have many advantages including low density, low cost, biodegradability, acceptable specific properties, improved thermal and insulating properties, and low energy in manufacturing, according to Pazia 2020. It is therefore practical to consider using municipal solid waste (MSW) for production of natural fiber because its ability to convert from waste into useful products and energy. In 2019, 19.9 million ton CPO production, according to MPOC, only 10% of gross palm oil consists of biomass, while the residual biomass is processed as a waste. It is about 90%, according to Awaluddin 2020. As Malaysia is one of the world's largest oil palm companies and experiencing robust growth through giant government companies. Abdullah Study 2013. This abundance of PEFB from garden is natural sources fiber and can be used in the polymer composite as a potential reinforcement, according to Faizi 2017. There are so many giant plantation companies, such as the example I given here is Felda, Simdabi Plantation, and also Felcra. My problem statement, one of the main problems experienced by the Department of Environment Malaysia is determining the best way to dispose of municipal solid waste MSW, particularly the garden waste of PEFB and plastic waste LDPE. The needs of high quality locally made material of deck panel are higher demand due to out of reach costly imported deck panels. The conventional deck panels are heavy and will increase the time for installations. Conventional deck panels that are heavier, high brittleness, and lower durability, according to Pelita 2016. Okay, I will continue with my research objective. The main objectives of this research are as follows. First is to determine PEFB fiber and LDPE plastic waste composition ratio into polyurethane resin and hardener to produce PEFB LDPE polymer composite. The second is to evaluate the physical properties and also mechanical properties based on different PEFB fiber and LDPE plastic waste composition ratio for PEFB LDPE polymer composite. And the third is to compare the performance of deck panel containing PEFB LDPE polymer composite with commercializing deck panel. To determine the optimum ratio of PEFB LDPE composition for decking panel, there will be a sample which is A, B, C, D, E, F, and G, and the ratio for PEFB fiber. Only for sample A, there will be no PEFB fiber, but for starting with B to G, there will be different ratio of PEF fiber with tagging with 0.1, 0.2, 0.3, 0.4, 0.5, and 0.6. For ratio of LDPE plastic waste, for all sample, the ratio is 0.2. For epoxy, for all sample, there will be 3, and the ratio of hardener will be 1 for all of the samples. To evaluate physical properties of fabricated composite for deck panel application. The physical properties will be evaluated using two types of tests, which is density and porosity, and also SEM analysis. For density and porosity, I am using ASTM D792 as a standard, and the specimen will be 3 specimens for each ratio. Total specimen were 21, and the diameter of the specimen will be 20 mm diameter and 3 mm thickness. For SEM, I'm using ASTM E76614E1 for the standard, and one specimen for each ratio. Total specimen was 7. Fractured sample from tensile strength test and for analyze the cross-section image. The dimension for SEM analysis sample will be 15 mm length and 25 mm width. For the third research scope is to evaluate mechanical properties of fabricated composite for decking application. For mechanical properties, there will be 5 types of tests, which is the first is tensile strength test using ASTM D3039. The second is flexural strength test using ASTM D7264. And the third is impact strength test using ASTM D7136. The specimen for 1, 2, 3 tensile strength test, flexural strength test, and impact strength test will be 3 specimens for each ratio. Total specimen for each ratio were 21. The dimension for the tensile strength test will be 20 mm width, 250 mm length, and 4 mm thickness. While for flexural strength test, 13 mm width, 150 mm length, and 4 mm thickness. And for impact strength test will be 150 mm length, 13 mm width and 4 mm thickness with 45-degree notch at the middle of the samples. For the fourth type of test, which is compressive strength test using ASTM D95, 3 specimens for each ratio. Total specimens were 21, and the dimension will be cylinder shape with 25 mm diameters and 50 mm length. And for the last test for mechanical properties is sound absorption test using ASTM E1050. 1 specimen for each ratio. Total specimen was 7. The dimension of the specimen will be 100 mm diameter and 4 mm thickness for lower range frequency, and 30 mm diameter and 4 mm thickness for higher range frequency. For the fourth research scope is to compare the performance of deck panel containing PEFB LDPE polymer composite with commercializing deck panel. The first is PEFB LDPE polymer composite based deck panel. It will be compared with Knauf bus fiber reinforced polymer composite, and will be compared with Knauf core fiber reinforced polymer composite. Okay, I will proceed with my literature review. Roslan 2014 using resin and hardener for the binder and the filler is PEFB plus fiberglass to design a test to improve flexural and tensile strength test of polypropylene. By Chancellor 2013 using epoxy resin with PEFB plus jute to compare the performance on energy absorption between different composite material using fiber-made sandwich arrangement. And Harshvardhan using urea formidable resin plus with plant waste, municipal solid waste plus sawdust, and also sawdust actually, to focus the utilization of all the filler in fabricating the particle board in the various ratio. Kasim et al. Using only filler as rock wool, aluminium can, and egg carton to investigate the utilization of recycled materials in producing the acoustic decking. The combination of rock wool and egg carton have better sound absorption compared to other combinations. Generon using concrete as a binder and its filler is waste coconut shell as a substitute for aggregates in developing concrete hollow blocks. Coconut shell and fiber are classified as miscellaneous material used for wall panel and partition. Purwanto 2017 using resin and methylethyl keton peroxide MEKP hardener as a binder, and its filler is polyethylene separated PET waste. This study determined the amount of filler of plastic waste in producing the panel board that can be used as wall building material, which are safe and does not require a lot of energy. Punyakan using concrete and its filler is industrial plastic waste such as high density polyethylene, low density polyethylene, and polypropylene. This studied the utilization plastic waste as an additional ingredient to improve concrete properties for precast concrete wall requirement, adding fiber content in concrete could increase the porosity and decrease the bulk density because hydrophobic property of the plastics. Eczema 2019 using epoxy resin hardener as a binder and its filler is pressed palm oil fruit fiber to study the physical and mechanical performance of the pressed palm oil fruit fiber reinforced with epoxy composite for decking application. Stated that the reinforced sample were lower than the pure epoxy matrix and density of the composite decreased as fiber content increased and indicate in achieving the lightweight matrix. And Suryani 2021 using epoxy resin and also pressed palm oil fruit fiber to study about the flammability and tensile properties of PEFB fiber for automotive use such as a car bumper. And what I'm going to study is using epoxy resin type DER324 with joint mass 9053S and the filler is PEFB palm oil M3 fruit bunch as a reinforced material in the epoxy matrix for deck application in this analysis. The PEFB ratio composition in the epoxy matrix was a key factor in determining the physical and mechanical efficiency. Let's continue with my methodology presentation. This is my flowchart diagram. We will start and preparing the sample. There will be 7 samples A, B, C, D, E, F, and G. For each sample, we will have a different ratio of PEFB fiber. Only for A. For B, they will be taking as 0.1, followed by 0.2, 0.3, 0.4, 0.5, and the last is sample G is 0.6. Ratio of LDPE plastic waste for all the 7 samples will be 0.2 equal all 7 samples, and ratio for polyurethane resin will be 3. Also equal all sample, and ratio of hardener also equal for all 7 sample. After I'm preparing the data, there will be a mixing process. All the sample will be mixed properly with all the ingredients, and after that will be the molding process. After the molding process are complete, there will be curing time. After all the 7 samples with the different ratio of PEFB were left about 24 hours for curing time, there will be 2 types of tests, which is physical test and mechanical test. For physical test, I will be done the density and porosity and also SEM analysis, while for mechanical test, there will be 5 types of tests, which is tensile strength test, flexural strength test, impact strength test, compression strength test, and sound absorption strength test. After all the tests are being made and the data are there, will be the data collection. And after the data collection been done, will be my result and analysis. After the result and analysis, there will be discussion and conclusion. Then end of my studies. Methodology for preliminary studies. Such as I said just before, there will be 7 samples of all, will be different ratio of PEFB fiber, but equal in LDPE plastic waste, epoxy, and ratio of hardener. This is my raw material, which is the above one is the PEFB, will be grinded, and the resin type I will be using the DER324. The epoxide equivalent weight is 119.5 to 204, and the epoxide percentage will be 21.1 to 22.1%. The viscosity around 900 to 800. The density is 1.1. The shelf life is 24 months. And for hardener, I'm using joint mine 9053S, and the chemical name of my hardener is modified polymer. Viscosity is around 200 to 400, and pot life is 75 minutes. And the amine value is 320 plus minus 20, and the density is 1.13 to 1.90, and the color of it is amber color. This is my fabrication process illustrations, which is 3 portion of resin plus 1 portion of hardener, and be mixed all the 3 plus 1 resin and hardener will be compute the sample A, while for sample B to G should be 3 portion of resin and 1 portion of hardener mixed with PEFB, different ratio for each sample, and will be produce the sample B to G with different fiber ratio. This is my sample preparation tabulation data of a different sample and different ratio of PEFB. This is my sample after curing process. The sample 0.1 is with 5 gram of PEFB, sample 0.2 with 10 gram of PEFB, sample 0.3 is 15 gram of PEFB, while sample 0.4 is 20 gram, sample 0.5 is 25 gram, and for the last sample, which is 0.6, is 30 gram of PEFB. And for the equipment, I'm using Sowell circular band saw for sample cutting process. And for tensile strength test, I'm using universal testing machine, using the standard ASTM D7264. And for density and porosity test, I'm using metal density and porosity kits using ASTM C2000. And for SEM analysis, I'm using scanning electron microscopes. And for bending strength test, I'm using universal testing machine using ASTM D3039 standards. And for compressive strength test, I'm using also UTM, universal testing machine, with the standard code is ASTM D695. And for the sound absorption test, I'm using impedance tube. And for impact test, I'm using CEAST 9050 motorized pendulum impact system. And I'm using the standard ASTM D7136. We'll continue with my result and discussions. PEFB LDPE epoxy composite physical properties. I will be discuss about two types of tests, which is the first one is density and porosity, and followed by SEM analysis. This is density and porosity graph, which is the black dotted line shows the average porosity and the blue dotted line is shows the average density. Okay, PEFB with the lower ratio 0.1 resulted in greater density of 1.1239, followed by ratio of 0.2 with 1.0914, ratio 0.3 with 1.0677, ratio 0.4 with 1.0591. The trend increased at the ratio 0.5 with 1.0690 and ratio 0.6 with 1.0794. According to Martini 2018, the existence of improved interfacial bonding with epoxy, as well as the reduction of microvoid by raising the composite density. The ratio of 0.6 PEFB LDPE had the greatest apparent porosity with 15.8%, followed by ratio of 0.5 with 13.7%, ratio 0.4 with 13.1%, and ratio 0.3 with 12.8%, 0.2 with 11.7%, and finally the ratio of 0.1 with only 8.6%. Due to an insufficient amount of epoxy resin and a greater viscosity, Lee in 2016 stated that the epoxy resin may not be capable of filling all the gaps formed between the filler particle with a higher filler content, resulting in flowability with a higher filler content. This is my SEM analysis picture, which is the sample A, B, C, and D. On the picture A, we can see the smooth exterior and also the cracked and wavy exterior. For picture B, we can see the broken fiber and pull-out fiber. Also the same with the picture C, pull-out fiber and broken fiber can be seen, same as the picture D. And for the sample E, we can see the pull-out fiber and broken fiber clearly, and also for the F and G. Many pull-out fiber in SEM image for PEFB LDPE ratio 0.4 to 0.5 and 0.6, indicating poor and weak interfacial bonding between the filler and the epoxy matrix. A SEM picture of 0.6 ratios reveal a cluster of fibers and patches with limited filler dispersion inside the epoxy matrix. A statement from Lim 2019, the absence of adequate epoxy matrix to allow efficient wettability of the filler leads to build-up of PEFB waste filler and micro space within the matrix. PEFB ratio 0.6 mechanical properties have been reduced because of poor dispersion of incompatible PEFB waste filler and its limited adhesion, according to Sabah 2019. The localized group of fiber and patches as seen in the SEM image of ratio 0.4 to 0.6 show poor filler dispersion within the composite. The number of broken fibers showed improved adhesion between filler and epoxy resin in the SEM image of PEFB LDPE ratio 0.3. We proceed with mechanical properties. We will go one by one, and with the first is tensile strength test, followed by impact strength, flexural strength, compression strength, and the last is sound absorptions. This is tensile strength versus different ratio of PEFB. The epoxy matrix of filler matrix was stable in terms of interfacial bonding, viscosity, and fiber dispersion in the epoxy matrix. PEFB ratio 0.3 sustained the greatest strength of 18.18 NPa. The tensile strength improved as the ratio grew. However, at PEFB ratio 0.4, 0.5, and 0.6, the trend showed the declines. Ratio 0.4, 0.5, and 0.6 PEFB show the higher tensile strength than those 0.1 and 0.2 ratios because PEFB can increase the strength, but it should not more or less, according to Rosland study 2018. This graph shows the stress versus strain for different samples of PEFB LDPE polymer composite. The maximum strain was 58% in the 0.5 PEFB LDPE sample, which might be happen because polymer composite matrix strong interfacial or cohesion bonding. According to Kolizadeh 2018, the interfacial adhesion between the matrix and the polymers has a big impact on the tensile characteristic of reinforced polymer. PEFB ratio 0.3 indicate that it has low strain and high stress, indicating that it has the brittle qualities and the highest strength. For impact test of PEFB LDPE, ratio 0.3 achieved the highest impact energy of 159.89. UTHM 2018 study results show the toughness of the composite can be improved by using the polymer composite into matrix. Barcelos 2014 study, the reinforced polyester matrix composite energy absorption potential has improved noticeably, and an addition of polymer to the matrix has increased the composite effect hardness dramatically. This graph shows the relationship between energy absorbed and impact strength test. As you can see, the dotted red line is showing the impact strength, and while the black dotted line is energy absorbed. For specimen 0.0, the energy absorbed is 0.09% and the impact strength is 0.98. For 0.1 sample, the energy absorbed is 0.18% while the impact strength is 2.04. For sample 0.2, the energy absorbed is 0.48% while the impact strength is 2.76. For ratio 0.3, the energy absorbed increasing for 4.4% and the impact strength is 10.10. For the ratio of 0.4, the energy absorbed is 0.92% while the impact strength is 5.36. 0.5 ratio energy absorbed is 0.48% while the impact strength is 5.35. For 0.6, the energy absorbed is 0.25% and the impact strength is 4.4. According to Javed 2010, by mixing PEFB as a filler, it will have the stronger impact strength, while the pure epoxy shows the weakest impact strength. With the PEFB ratio in the epoxy resin until 0.3, the energy absorbed increased steadily. 0.4 until 0.6 show the decreasing energy absorbed trend. This graph shows the flexural strength test. First page shows the appearance of the linear can be used to describe the composite elastic deformation. Second phase shows the connection between displacement and load is not linear. PEFB LDPE ratio 0.3 with 44.92 mm shows the maximum deformation value for ductile mode. The second highest value ratio 0.4 with 44.17 mm and followed by ratio 0.5 with 42.6 mm, 0.2 42.4 mm and 0.5 41.04 mm with the deformation of 37.17 mm. 0.1 PEFB LDPE achieved the lowest deformation. This result shows the composite having a large proportion of PEFB should exert extra resistance until it progressively broken or pushed out of the fully ruptured matrix as stated by Gabriel's study 2017. For the flexural strength test, the flexural strength test rose until the PEFB ratio reached 0.3, then dropped somewhat after the ratio reached 0.4. Ratio 0.3 was able to withstand the greatest flexural strength of 26.202 MPa, followed by ratio 0.4 with 24.6 MPa, ratio 0.5 with 24.3 MPa, and ratio 0.6 with 24.13 MPa. Ratio 0.2 with 17.64 MPa, and the ratio 0.1 withstood as the lower flexural strength with just 13.46 MPa. For the compression strength test, the filler epoxy matrix interfacial bonding was extremely poor at the PEFB ratio 0.6. The sample were determined to be rigid due to an excessive amount of filler inside the reinforcement. Climbing trends occurred up to an PEFB ratio 0.3, then significantly reduced from 0.4 to 0.6. The highest value of compressive strength was obtained by PEFB LDPE ratio 0.3 with 12.59 MPa, followed by ratio 0.2 with 7.61 MPa, ratio 0.3 with 9.09 MPa, ratio 0.5 with 5.68 MPa, ratio 0.6 with 4.9 MPa, ratio 0.1 with 4.31 MPa. The control sample ratio 0.0 get 2.86 MPa. Marlish 2019 stated that the fiber and frictional additive in combination with the binder produced a good contact between particles and binder since the filler was equally distributed throughout the composites. For the sound absorption test, many variables influence the sound absorption in composites, including air, flow resistance, porosity, viscosity, density, thickness, and tortuosity, based on Ismail's study 2019. The sound absorption coefficient of the control sample with no PEFB had poor sound absorption, with a sound absorption coefficient SAC of less than 0.3 throughout the whole frequency range of 100 to 5000 Hz. The highest alpha was achieved by PEFB LDPE ratios of 0.6 with SAC of 0.87 at the frequency of 1250 Hz. PEFB LDPE of 0.3 was at 0.5 at the frequency of 1250 Hz, but the alpha increased to 0.59 at the frequency of 2000 Hz. Lee 2017 stated that the material is considered sound absorbent in the average if the average sound absorption coefficient is greater than 0.2 after all 5 major frequencies have been calculated. Ratio 0.3 after all the 5 major frequencies have been calculated, getting the alpha of 0.29. This is for the comparison mechanical properties of polymer composite PEFB LDPE with Knauf bus fiber and Knauf core fiber. The table shows the comparison tensile strengths of the PEFB LDPE composite with Knauf bus and Knauf core. From the graph, it can be concluded that PEFB composite had higher tensile strengths with 18.18 MPa compared to the Knauf core, just 16 MPa, and the lower tensile compared to the Knauf bus with 19 MPa. According to Maynard 2021, Knauf bus fiber have a cellulose percentage of 60.8%. However, it is found cellulose level of 50.6% in the core fiber. This could be concluded why Knauf bus has higher tensile rather than Knauf core, but also the Knauf bus cannot compete with the PEFB LDPE polymer composites. For Flexurous test result comparison of PEFB LDPE with Knauf bus fiber and Knauf core fiber, the flexural strength ratio of 0.3 PEFB LDPE composite was 44.92 MPa, which showed the maximum deformation value for that time mode. The flexural strength test had been carried out using 3-point bending strength in comparison with Knauf bus and Knauf core. Unlike tensile strength, for flexural test, Knauf bus and Knauf core get a higher value of 10% with Knauf bus at 37 MPa while Knauf core at 28 MPa. This could be concluded that PEFB LDPE get a higher flexural strength result and more static at the ratio of 0.3. The table shows the result by Ishaq for Knauf bus and Knauf core flexural strength test and be compared with my study, which is PEFB LDPE polymer composites. This graph shows the impact test result for different fiber, which is PEFB LDPE, Knauf bus, and Knauf core. The PEFB LDPE composite impact strength was evaluated and discovered that the best ratio was 0.3 with 44 MPa, while the best tensile for the Knauf bus that been studied by Ishaq only had 34 MPa and the Knauf core only 24 MPa. This was due to improved stiffness and energy absorption during the fracture of the ratio 0.3 PEFB LDPE composite due to strong interfacial bonding between epoxy resin and PEFB waste. Duan 2018 stated that for the Knauf bifiber composite, the ideal value for obtaining the maximum impact strength was 10%, whereas for the Knauf core fiber composite, the optimum value was 5%. But with the 10% of the Knauf bus and the 5% of the Knauf core, PEFB LDPE still get the higher impact test result. As a conclusion, the use of municipal solid waste mixed polymer composite-based palm empty fruit bunch waste as a partition panel or deck panel has been effectively addressed. The PEFB LDPE composite have the high physical and mechanical properties and are suited for use in decking panel preparation because of the physical and mechanical performance of PEFB LDPE composite have been proven by tests. PEFB LDPE composite ratio 0.3 attained the best ratio compared to other ratio. PEFB LDPE ratio 0.3 had a density with 1.0677 while the apparent porosity with 12.8%. Ratio 0.3 also had been proven the greatest among other ratio by SEM analysis. PEFB LDPE had the maximum tensile strength with ratio 0.3 which is 18.18 MPa. 0.3 PEFB had the lowest strength percentage which is just 3.28%. Ratio of 0.3 PEFB LDPE also had the greatest impact test result with 159.89 and the energy absorbed is 4.4%. PEFB LDPE ratio 0.3 was able to withstand the greatest fractural strength of 26.202 MPa and showed the maximum deformation value for ductile mode with 44.92 mm. The highest value of compressive strength also obtained by 0.3 with 12.89 MPa. PEFB ratio 0.3 was 0.50 at the frequency of 1215 Hz and the alpha increased to 0.59 at the frequency of 2000 Hz. PEFB have the highest strength for tensile strength test, fractural strength test, and the impact strength test compared with both Knauf fiber and Knauf core. The use of PEFB LDPE reinforced with epoxy resin in the fabrication of decking panel was appropriate, since PEFB LDPE outperformed both Knauf bars and Knauf core mechanically and physically. This is some of my references. Continue. This is my sums of my publication, which is recycling types of municipal solid waste for bioproduct developments and on characteristic of bending strength of plastic waste, reinforced wood waste for polymer composite, which is Copper Journal, characterization of wall partition bioproduct from plastic waste, reinforced polyurethane form composites, development of tile bioproduct from plastic waste, reinforced wood waste composite, and also utilization of plastic waste reinforced wood waste composite for tile application, which has been published on the year of 2021. This is one of my award achieved for the invention titled Municipal Solid Waste Polymer Composites, which is Gold Award. That's all my presentation. I hope you like it. Thank you. And I end my presentation with Assalamualaikum warahmatullahi wabarakatuh and very good day to everybody. Thank you.